Chapter 17, Lesson 5. In this chapter we've been talking about acids and bases for the most part, and we'll finish up with a discussion of solubility products. Now these will relate to acids and bases because, as you'll see, the substances that we'll talk about will have basic or acidic parts to them. So the solubility products are referring to ionic compounds that are not soluble in general. If you take a look at barium sulfate is not soluble. In fact, barium is, along with calcium and strontium, if you recall, one of the bandits, because sulfates are usually soluble in solution except when in contact with one of these group 2 ions. So barium sulfate is a solid. However, any solid can be very slightly soluble. So if you put any solid in solution, a tiny amount of it will dissolve. And now we can express this with an equilibrium system. And then they will dissolve into barium 2+ and sulfate 2-. If we set up the constant for this, we will see that K will equal just the products because our solid does not go into equilibrium expressions. So we end up multiplying the two products. And this is why this is called the solubility product. KSP is the designation. So anytime you see KSP, in fact there are plenty of KSP values in Appendix D of our book. And most books will have KSPs listing the insoluble substances. So we can use these KSPs to do quite a bit of work for us, or to give us some important concepts. But in this problem, why don't we try to calculate the KSP? And how would you calculate a KSP for a substance? Well, you simply measure how much is found in the solution at equilibrium. In this case, we have silver chloride, which again, remember, silver is a robber of group 17 ions. So this is not soluble. A tiny bit amount of it actually is. And this is exactly how much is soluble. So if you think about, you got a beaker here that's a bit on the wobbly side, but if you put some of this solid, even though most of it will not dissolve, and most of it will go to the bottom of the beaker, a little bit of it will dissolve, and that little bit is given to us here. So now we want to calculate the KSP for this substance. Let's go ahead and treat this as an equilibrium because KSP refers to equilibrium. So we have silver chloride as a solid dissociating into silver plus and chloride minus. Let's set up the icebox. This will be an icebox style problem. Really, every equilibrium problem can be set up as an icebox problem. Now, for the silver chloride, because it's a solid, we won't include it in the equilibrium expression. However, we're going to still keep track of it in our icebox. This will make things actually a little easier. And you'll see I'll put just a shaded amount of it, because it doesn't really matter how much we begin with it. We have some amount of it beginning. You can put a number in there if you want. You can put 10 in there or whatever you want. But I'll do it like this. So at equilibrium, or initially, we have nothing in the solution for the icebox. Then once we put silver chloride in there, there's a change that happens, and then we come to equilibrium. Well, we find that at equilibrium we have 1.35 times 10 to the negative 5th present of silver. So we'll put that here, 1.35 times 10 to the negative 5th. Now, in order for us to get this much, we must add 1.35 times 10 to the negative 5th. If we added that here, we must add that on the chloride side as well, since it's a 1-to-1 ratio. And then we must subtract that much on the silver chloride side, minus 1.35 times 10 to the negative 6th. So we can see at equilibrium we have some amount of it minus 1.35 times 10 to the negative 6th. That's really how much we lost. And here we have simply 1.35 times 10 to the negative 5th. Now we really won't be dealing with this side of it, so we can cross it out for the time being, even though it's convenient to still list the amounts. And now we're asked for the KSP. Well, K is simply products over reactants. Because our reactants are solid, we don't have to include them. We end up simply doing 1.35 times 10 to the negative 5th multiply by itself. So let's square that and go ahead and evaluate this into your calculator. And you should get 1.82 times 10 to the negative 10. And this is your KSP value of silver chloride. This is what you should find in the back of the book or in similar reference volumes. So now this actually gives us, the KSP indirectly gives us the solubility of silver chloride. It gives us it in terms of equilibrium. So solubility products, the KSP is not the same as solubility, but it is related. Solubility, if you recall from chapter 4, is usually given in grams per volume, usually grams per liter, could be in grams per milliliter, sometimes it could be in moles per liter, but you can go between the solubility, grams per liter, to KSP, because KSP, remember, is simply the multiplication of the two molarities. So if you go from grams per liter to moles per liter, then you can go from moles per liter to KSP, because KSP simply takes the moles per liter and squares it. And then you can also go the other way. You can go this way. So solubility and KSP are related, and we will take a look at some of this relationship in a little more detail. Now we will mention something. Let's mention something called the common ion effect, and these are some factors that will affect the solubility of ionic compounds. In fact, even though barium sulfate, the one we began with, is not very soluble in water, it's a solid, we can actually get all of it to dissolve in the water if we wanted to. And this has to do with the common ion effect. This is very similar to what we began talking about when we started talking about buffers. This includes having something in solution already with your substance that you're discussing. So here it says if one of the ions in a solution equilibrium is already dissolved in the solution, the equilibrium will shift left and decrease the salt's solubility. So here's barium sulfate. At equilibrium we have a lot of reactants and very little bit of the products. However, if we were to add more sulfate to the solution, the equilibrium will further shift to the left to try to remove some sulfate and then decrease our amounts even more. And that's kind of the idea. And we can also remove sulfate from solution, and we can get it to go to the right. So you can actually do either thing. So why don't we do a little calculation of this. Here it says calculate the molar solubility of calcium hydroxide in a solution that already contains some sodium hydroxide. Now sodium hydroxide is very soluble, and calcium hydroxide is not. Calcium hydroxide is a solid. So we can set the solution up with already some present ion, and that will affect the solubility of calcium hydroxide. Let's go ahead and do this as an icebox, and the icebox will be referring to calcium hydroxide. Now, so we have calcium hydroxide in equilibrium with its two ions, calcium 2 plus and hydroxide minus. Now this is important to be able to balance the equation. So notice we have two hydroxides. This will actually affect our answer. So we have to make sure we balance the equation. Now the KSP of the salt can be found in the back of the book. So consult your Appendix D in the back of the book. And you should see that this is 6.5 times 10 to the negative 6th. If you don't have an Appendix D, you can just Google the value, and hopefully the web will have, among all its constants, calcium hydroxide's constant. Well, let's set up the icebox as we've done before. Calcium hydroxide is a solid, so it won't go into KSP, but let's keep track of it nonetheless. This will make things a little easier. So we'll say we have some sort of amount of calcium hydroxide. It doesn't really matter what amount. Remember that in solution, what we have is we have a beaker in which we have a chunk of solid at the bottom, and only a little bit of it dissolves. And that's essentially our situation. So in contrast to the previous case, what we've got is we have a little bit of hydroxide already present. So we will have 0.010 initially present of hydroxide and nothing of the calcium, because initial, what we mean by initial is the point at which we just throw the solid into our solution. Equilibrium is the point at which we now have a bunch of dissolved solute. So as we get to equilibrium, we must lose on the calcium hydroxide side and gain on the product side. Now here we'll have to gain 2x. Here you'll have to be careful with your insoluble substances that have 2 anions. So for equilibrium we have some amount minus x. Again, we won't really care about this side as much because solids don't go into equilibrium constants. But we have an x here, and we have 0.010 plus 2x. Let's go ahead and set this up to solve for x, and we have 6.5 times 10 to the negative 6th equals x multiplied by 0.010 plus 2x quantity squared. We'll have to square this still because of this 2. So these icebox calculations come back to chapter 15 where we considered the coefficients. So this is a little more complex. In fact, if you were to try to solve this using standard methods, what you will find is you have a cubed term. You'll have an x cubed term, which will provide a lot of fun or difficulty trying to solve an x cubed term. So what I would do in this case is use our old rule of ignoring x, because x in this case will be so small compared to our KSP. We have 10 to the negative 6th. This number here is 10 to the negative 2nd. We are within 3 orders of magnitude at least. We actually more than that. So we could justify ignoring x. And so this will make our problem quite a bit easier. So really we have 6.5 times 10 to the negative 6th equaling 0.010x. Now this 0.010 will have to be squared like this. We just rearranged it. So in fact, maybe it's a bit confusing, but these two are just rearranged. So really, to solve for x, we just have to do 6.5 times 10 to the negative 6th divided by 0.010 squared. So x, if you compute this in the calculator, go ahead and put this into the calculator and see what you get. And you should get x to be 0.065, which is a small number. However, that is would be, so x would be the amount that is dissolved in this case. So hopefully this this little problem made sense. X would be 0.065. Now x, so what we calculated for here, x, is how much of the calcium hydroxide actually dissolved. So this x is really how much of the calcium hydroxide in solution went into the solution. That's essentially what we have been solving for. So hopefully this one makes sense. We can massage it a little more as we get to class. Some more considerations about the factors affecting solubility, and these considerations have to do with pH, because in this chapter for the most part we've been talking about acids and bases, and if your salt, your substance, has a basic anion, this means our barium sulfate, for example. Sulfate is basic because it came from sulfuric acid, H2SO4. And then since it's basic, it'll be more soluble in acidic solution. Acids will actually affect its solubility. And then conversely, if you have an acidic cation, that will become more soluble in basic solution, which makes sense. So here's a picture of what we're talking about. Here's magnesium hydroxide, a substance that's not soluble. However, if you put it into acid, the H+, will neutralize the hydroxide and make it more soluble. And then you'll get a bunch of magnesium sulfate, magnesium 2+ in solution. Again, the idea is the hydroxides in magnesium hydroxide can be neutralized by the acid. So here's a picture of it. If you were to try to dissolve magnesium hydroxide, you just get yourself a bunch of precipitate at the bottom, but if you add some acid to it, all of it will dissolve. So your basic anion is more soluble in acidic solutions, and conversely for the acidic cation. So we can ask a question like this: which of the following substances will be more soluble in acidic solution than in basic solution? So if you take a look at nickel hydroxide is a solid, so for the most part it's not soluble, so its equilibrium would look like this. You don't have to write it out, but this is going to be easier seen. Technically, if you put this in H+, if you were to add to the system some H+, that H+ will take care of the hydroxide and move it out. It'd be like if you're removing hydroxide minus. Because this is an equilibrium system, the system shifts to the right to replenish some of that removed hydroxide, and so more and more of the nickel hydroxide dissolves. So nickel hydroxide, having a basic anion, is more soluble in acidic solution. Calcium carbonate also has carbonate, which is basic. Remember, carbonate is the conjugate base of eventually carbonic acid. From carbonic acid you'll get hydrogen carbonate, and from that you can get your carbonate, which means this is basic, so it'll be much more soluble in acidic solution. Same thing here for barium sulfate. This will be more soluble also in acidic solution, because sulfate is the conjugate base, you can say, that comes from sulfuric acid. Now sulfuric acid is strong, however its second hydrogen is actually much more weakly held. So when you come out to SO4 2-, this substance is considered a base. So you can actually get more of it dissolved in acidic solution. Now if you take a look at silver chloride, it's also solid, however chloride is not a base. It's the conjugate of HCl, which is a very strong acid, very strong. And so neither acid nor base will affect it. So actually here we'll say neither for silver chloride. And hopefully this idea makes sense. Let's finish up with a discussion of something called complex ions. It turns out that further solubility can be achieved by something called coordination complexes. These are actually very interesting, very strange, but very interesting substances. So anytime you try to dissolve a substance in solution and it doesn't dissolve, you could add a special complex, a special substance to make it dissolve. And the way you do that is you'd have to study these salts, but many salts, especially salts coming from the D block, this is cobalt, because most of these are not soluble, but many D block ions have the d orbitals opened up to them. Recall that the d orbitals, there are 5 d orbitals, and those can hybridize and essentially create areas of bonding between substances. So this essentially happens with D block ions because of this opening up of the subshells, D subshells, the 5 D subshells. And in this case what you see ammonia, which is able to dissolve cobalt. Now this would be in solution, and you'll find the solubility of substances all of a sudden going up in solution because of this idea of formation of coordination complexes. This is a kind of a strange idea, but here we have silver chloride. Again, this is your insoluble substance. This is what we couldn't dissolve previously with an acid or a base because it doesn't have a basic anion. You can, however, still do it with something like ammonia and other substances, because ammonia will form a complex with these. It'll take and it'll remove and pull the silver up into the solution. So you get yourself a silver complex that looks like this. You essentially have silver, Ag, surrounded by two ammonia molecules. It's as if the ammonia pulls up and decides to dissolve. The water can't dissolve the silver, so the ammonia decides to dissolve the silver, and that's essentially what happens. And these coordination complexes will have their own K values. Oftentimes this is referred to as Kf, F meaning the formation of the complex. And notice silver is usually insoluble, but if you put it in ammonia, you can get it to be quite soluble. These Kf values are very high. Notice how huge they are. These are the inverse of your Ksp values. So you can also add some cyanide if you want and get silver to dissolve. You can add some thiosulfate and get silver to dissolve, and on and on. There are plenty of these. So this is a way of dissolving substances that don't really have basic anions. So very common are among these are NH3. NH3 is a common substance. Cyanide and thiocyanate here, or thiocyanide, so these are fun, and maybe we'll show you a few of these in class. But this would conclude for us lesson 17 all together. And hopefully you've enjoyed it, and we will see you next lesson.